Hey guys, it is GreenDome team. Currently, access to fresh fruits and vegetables is crucial to stay healthy. That is why people need to grow plants permanently the whole year. Today's greenhouses are outdated, inconvenient to maintain, and harmful ecologically. And we found the best solution, GreenDome.
There are many benefits of our heating system over the existing solutions for the problem. But why our project is the best solution for the problem? Firstly, our project is not only 2, but 3 times efficient than other common heating systems in the world. Secondly, our project doesn't have any detrimental impact to the environment, as it doesn't consume fossil fuels. Thirdly, there is an extremely convenient and technological maintenance for greenhouse due to the remote control of UV, for photosynthesis and temperature, humidity and soil sensors.
Unfortunately, there are some flaws in our project. First one being the high budget needed to build such a complicated system. Second one is a subsequent problem with freon leaks, which could then lead to the collapse of the whole system. Third, and the main one, is the constant need for electric supply to keep the crops growing.
We have compared all existing heating analogs and defined the gas heating system as cheapest option. There is short comparisons of gas and GreenDome systems. There is no doubt that gas is the most popular choice among farmers due to its low cost and ease of setting. However, just thousands tenge, GreenDome can offer rational consumption of electricity, ecologically safe heating, and total remote management.
Our device is a smart system designed for real-time soil monitoring. It measures the 5 key factors for healthy plant growing. It is soil and air moisture, light level, pH, and temperature. All data is transmitted to a mobile application where farmers can view current soil conditions and receive personalized recommendation for fertilization and irrigation. When the soil becomes too dry, the system automatically activates irrigation, helping to prevent drought stress. Our device is powered by a solar panel, and in greenhouse environments it can also run on main power or with internet connection for expanded control. Unlike existing systems that offer only one-time analysis before planting, our device provides continuous monitoring throughout the growing season. It reduces fertilizers and water use up to 30%, while increasing average yields by 25 to 30%. The device is affordable, weather-resistant, and designed to improve both soil assessment and production quality.
The principle of our system. The refrigerant and water cycles are designed to compensate for heat losses. And suppose I have the outside temperature of minus 20 Celsius degrees, and we are required to heat up the temperature by 40 Celsius degrees. Using the formula U equals 10 multiplication of U, A, and delta T, where U is a heat transfer coefficient, which is 2.5 watts per square meter Celsius, and A, which is the surface area of our greenhouse, which is 130 square meters, and the last one, delta T, it's the difference of temperature. As I said, it's 40 Celsius degrees. And calculating the heat loss, it's a multiplication of 2.5, 130, and 40. It gives us 13 kilowatts per hour. But although the actual heat loss could be as high as 20 kilowatts per hour. And they significantly reduced due to seal structure of greenhouse and usage of double layer polycarbonate panels, usage of thermal curtains, and installation of lower height of the greenhouse. And as a result, the final estimated heat loss is 13 kilowatts per hour, and our system is designed to compensate these heat losses.
The first stage of the cycle is evaporation. The system is designed to compensate for heat losses by utilizing low potential thermal energy from the ground at a depth of 7 meters. The refrigerant absorbs approximately 10 kilowatts of thermal energy from the source and evaporates, reaching a temperature of 5 degrees Celsius. In the second stage of compression, the refrigerant enters the compressor. Given that the coefficient of performance is around 4, the system generates 4 times more heat energy than the electric energy consumed. Only the compressor requires electricity, consuming 3.25 kilowatts per hour, while the remaining thermal energy is sourced from the ground. During compression, the temperature of the refrigerant rises sharply to between 40 and 60 Celsius degrees. The use of a natural refrigerant with excellent heat conductivity, the relatively small temperature difference between the ground and water, and minimal heat losses all contribute to the system efficiency. In the third stage of condensation, the refrigerant transfers its heat to the water, raising the water temperature to 40-50 Celsius degrees, and condenses back into liquid. This heated water is then delivered to the greenhouse to compensate for heat losses. After releasing the heat, the refrigerant cools down to around -5 Celsius degrees and is returned underground, completing the cycle.